for the fact at different possibilities for whether it's sales or whether it's price or whether it's the cost of production or whatever. We might consider that some sort of distribution on the different values that they may have. So here would be the expected return, and I'm going to speak in terms of investments, but this is going to apply to corporate finance. The expected return, if you have some set of probabilities, is equal to, and you've seen this summation sign, right? This big sigma means add them up. So it says take the sum of the different probabilities times the different returns. Each return times its probability of occurring. So here we have a distribution. I is just this index. That just means we have 5 different possibilities. And the different possibilities of return in this case, and you just don't throw numbers on, you actually come up with why might there be such a return as 10% or minus 10% or whatever. But in this case, we're saying the return is minus 10%, and there's a 10% probability of that. So we've got returns in this column, we've got probabilities in this column. Minus 10% has a 10% probability, a 0 return has a 20%, a 10% return has a 40% probability, 20% return has 20, and 30% has 10. Now, this is a nice kind of pyramid of a distribution, because these are all 10 units apart here, and this is a nice little pyramid. 40% in the middle, 20 on either side, and 10 in the tail. So it's kind of like a normal distribution, kind of like. So if we want to figure out what the expected return is, we just multiply the probabilities times the returns and get those products. That's what this says. It says take the PI times RI, okay, for each one of them. Okay, for I equals 1. PI times RI is 0.1 times 0.1, a negative 0.1, which is negative 0.01. So 0.1 times 0.1 is 0.01, and this is a negative, so it's negative 0.01. And the next one is 0 times 0.2, and that's a 0. Then we got 10.1 times 0.4, that's 0.04. The next one's 0.04. The next one is 0.03. So everybody see where these numbers are coming from. And then all we do is add them up. So the summation sign here says, okay, you got all those products. Now add up all 5 of the products. And when you do that, you get 10. Well, this is such a nice little symmetrical distribution. We could see that it was going to be right in the middle of 10 just by looking at the distribution. But when you do the actual calculation, you see that it's 10. Now, to calculate the standard deviation is a lot more complicated. So think of this word deviation, standard deviation. Well, let's start with the word deviation. The deviation part says, what are the deviations from the mean? And in this case, the mean is the expected return, because we're talking about all these guys here are returns. So this is the expected return, 10%. So our standard deviation, we're going to start by saying, well, these different returns, how much do they deviate from the expected return? So in this case, the expected return is 10%. And this return for outcome I equals 1, this return is minus 20. So what is the deviation? Well, this part in parentheses here, right here, says return I minus the expected return. Return I minus the expected return. Well, return I for I equals 1 is minus 10. So minus 10, and we're going to subtract the expected return. So minus 10 is minus 20. We go to the next one, and it says 0 minus 10. 0 minus 10 is minus 10. Then 10 minus 10 is 0. 20 minus 10 is 10. And 30 minus 10 is 20. Everybody see where that stuff's coming from? We good with that? Okay. So now we have all those different deviations from the mean. Deviations from the mean. Now we're going to square each one of them. So this minus 0.2 squared is 0.004. Everything that gets squared, we're getting rid of the minus sign. So we've got 0.2 squared is 0.04. Sorry, minus 0.2 squared is 0.04. Minus 0.1 squared is 0.01. 0 squared is 0. 0.1 squared is 0.01. And 0.2 squared is 0.04. Now it's nice and handy for us because of this nice simple distribution that these two guys up here are just like these two down here. So if we have a nice little symmetrical pyramid kind of a distribution, it makes it easy to check yourself if nothing else. Okay, so what we have now is all those squared deviations. Squared deviations. So that's what this says here. Up here it says take the deviations and then square them. That's what that thing says. Then it says, okay, now multiply them by their respective probabilities. So this 0.04, we're going to multiply it by this 0.04, we're going to multiply it by this probability, 0.1, and that gives us 0.004. 0.2 times 0.01, 0.002. 0.4 times 0 is 0. 0.2 times 0.01, 0.002. 0.1 times 0.04, 0.004. So, now we've got all the probabilities times their respective squared deviations from the mean. And then this says, okay, now add them up. That's what the summation tells us to do. So that's what we're going to do. We're going to add them up. And when we add them up, we have the variance. Now, when we take the square root of the variance, we get the standard deviation. So, it says, first, figure out what the expected return is, then calculate the individual deviations from the mean, square those deviations, multiply those squared deviations times the probability, add up all of them, and when you get to that point, you've got the variance, and take the square root, and you've got the standard deviation. Okay, you go with that? Okay, let's go to the next one. Now, this next one is going to be kind of handy for us. Because we can use our cool calculators to figure some of this stuff out. Okay, so have your handy calculator handy. Okay, this says the mean return. Now notice the other one was expected return. We were looking from before. Now this is ex post, after the fact. So on an ex post basis, what is the mean return? Well, we're going to do what you did in third grade, which is add them up and divide by however many of them there are. And that's all it says here is take all the individual returns, add up all the individual returns, and divide by n. N is just how many of them there are. So, here's a different case. It says returns over time. Now notice I've switched from I to T. T generally you use when you're talking about time frame. So this is time period 1, 2, 3, 4, and 5. And I've got returns that are different in the different time periods, 12, minus 12, 24, 10, and 16. And the mean says, take all the individual returns, the return for this thing in time t, for each one of them, add them up, divide by 5, and you get 10. Okay, so that's our mean return. Looking historically over this, we've got a mean return equal to 10. So let's calculate the standard deviation. Well, this form is a little bit different. You see, it doesn't have a probability in here. The reason is, all these things occurred with 100% certainty. It's not like we think there's a probability of 20% that it'll occur next year. No, we know it did occur 2 years ago. That was the actual return. So we don't have the probabilities in here. We do the standard deviation a different way, just like we did the return a different way. Here's how we do it. It's actually maybe a little bit easier. we take our deviations from the mean, just as we did before. We square the deviations from the mean, just as we did before. But instead of multiplying them by their probabilities, we end up dividing them all by n. So we're going to take these deviations, square them, add them up, divide by n. No probability is included in this. So here's how it looks. We've got 12 return here and a 10 mean. So 12 minus 10 is 2. Minus 12 minus 10 is minus 22. 24 minus 10 is 14. 10 minus 10 is 0. 16 minus 10 is 6. So everybody follow where that stuff's coming from. Okay, now it says, okay, you've got that those deviations. Let's square the deviations. 0.02 squared is 0.0004. 0.22 squared is 0.0484. 0.0196, 0, and 0.0036. Add them up, because that's what it says to do. And then divide by n. Now, key point here. You divide by n if it's a population. And you divide by n minus 1 if it's what? Sample. Okay, n or n minus 1. I'm going to follow through here with n, but actually your book uses n minus 1. So if you're looking at a sample, why is it that you would use a sample? Because you don't have them all. You're just taking a part of it, and then you lose a degree of freedom. And by the way, what's that going to do to my standard deviation if I divide by n minus 1 instead of n? How is it going to compare its size?
You'll be greater.
Okay. If your denominator is a smaller number, then the answer is going to be a bigger number, right? Okay. So we've got all these numbers. We add them up and divide by n, and that gives us our variance. And then we take the square root of it. That gives us our standard deviation. So generally, we're going to say standard deviation. That's for a population, and S would be for a sample. And that means we're using divide by n minus 1. Okay, we go with that so far? Okay, now, pull out your calculator. And it's always good to turn it on. Except when you're putting it away. So here's how we're going to do standard deviation. We're going to take these numbers and put them in our calculator in a certain way so as to get the standard deviation. Here's how it works. Press the second key and the 7, that's data. Okay, now I have a lot of stuff in here and I need to get rid of that stuff. So second, and hold on a second. Does yours have any stuff in it? Hit the down key. Unless you've done this before, it should. So now let's get to X1. And we're just going to do X's. You could have X's and Y's in here. We're only going to have X's. So we're going to insert.
My contact are up.
Oh, okay. Sorry. I wore them for many years. I understand. So we're going to insert all the X values, and these are the X values. And for the Y values, we're just going to put in 1. Or 0 flat. So we're going to put them in one at a time. So 0.12, enter, down. And now it's saying, well, okay, what's the Y value? Well, let's just leave it at 1. So then hit enter, down. So now it should say X, 2, and 0. Are we there? Okay. Then 0.12 negative, 0.12, change signs, enter, down, and again, y2 will be 1, so we'll hit down again. Then x3 is 0.24, so 0.24, enter, down, down. 0.10, enter, down, down. And 0.16, enter, down, down. Okay, are we good there? And now it says x06 is 0. Okay, now, hit the second key and the stat key, which is 8. And actually, this is taking us into linear regression. Did you do that in stat statistics? Okay, but we're not, that's not what we're concerned about with this right now. We're just looking at standard deviation. So now press the down key once, and it says n equals 5. Okay, we know we're on the right track because we know there were 5 of them. Hit it again, and it says x bar, the mean value of x, is 10.10. Well, that's what we got when we calculated before by hand. We're going to go down one more, and it says Sx, that's the sample, is 0.1341648. We go down one more, it says the sigma x is 0.12, which is what we did calculate before. Okay, you good with that? So calculating standard deviation on the calculator, pretty handy?
Yeah.
Okay, good. Now, while we're talking about returns, I want to talk about the geometric mean return, the geometric mean return. And before I even do that, let's talk about what returns there would be if you invest money. That is, I put money in, and then a year later, I have more money. So how do I figure out what my returns were? So let's say that I start at time zero, and I go to time 1. And let's say that I have a value at time 0, and at the end I have a value at time 1. So my investment has increased in value. Forget about dividends for a while, we'll just talk about the value that we have at the end. Well, we would call V1 over V0 a holding period return relative. Holding period return relative. If we took just the change in value, that is V1 minus V0 over V0, that would be the holding period return. Now, note that the holding period return could be restated as V1 over V0 minus V0 over V0. See that? We've got the denominator here, and we've got, we're just splitting this out, showing V1 over V0 minus V0 over V0, follow me there. And that's equal to V1 over V0 minus 1. So the holding period return then can be expressed as the holding period return relative, which is what this is, minus 1. So the holding period return equals holding period return relative minus 1, or the holding period return relative equals, I will go ahead and say 1 plus the holding period return. So if you start with $100 and you end with 106, your holding period return relative is 1.06, 106 divided by 100. Your holding period return, that's your holding period return relative. Your holding period return would be 106 minus 100, that's 6, divided by 100, 6%. Now you might ask yourself, why bother with this holding period return relative thing? Well, here's why. If we want to figure out returns over time, we don't use the arithmetic mean, we use the geometric mean. And the geometric mean requires that we use the holding period return relative. Now, I'm going to give an example here. What would happen if I started with, let's just say $100, and that's at time 0. And at the end of time 1, I had $200. what rate of return would that be? Just holding period return, not relative.
100%.
100% return, that make sense? Okay, it's 100% return. Okay, the end of the second year, my 200 drops down to 100. What rate of return is that?
0.
Okay, minus 50%.
Yeah.
Okay, what's my mean return then?
75%.
Add them up and divide by 2.
Yeah.
25%. 100 plus minus 50 divided by 2, 25%. Okay, so I'm your financial advisor, and you gave me $100. 2 years later, it's still $100, and I'm telling you that your annual rate of return was 25%. Do you buy that?
No.
Doesn't seem like you made a whole lot. You started with 100, you still have 100. Well, the way the geometric mean works is you take the holding period return relative. So instead of 200 minus 100 divided by 100 to give you 100%, we just say 200 divided by 100. And that's the holding period return relative for the first year. In the second year, it's 100 divided by 200. So that's just this holding period return relative, this thing up here. And so now what we're going to do is take a geometric mean. So pull out this thing here on page 2, and this gives how you calculate the geometric mean. So what this says is take 1 plus the rate of return in decimal form. So 1 plus the rate of return, well, that's the holding period return relative. So we just showed how you come up with that holding period return relative. So this is a holding period return relative. And this says to get the geometric mean return, you take all the holding period return relatives, and now this isn't a sigma, it's not a sum, it's a pi. So what does this tell us we're supposed to do? It's not pi like pi r squared 3.1459, whatever it is. Pardon? You multiply all the values together. So the sigma says add up all this stuff. The pi says multiply. So it's like sum, sigma for sum, pi for product. So we're going to take the product of all the holding period returns. Product of all the holding period returns. Okay, so what does that mean for this one? I said holding period return relative. Take the product of the holding period return relative. So here's the first holding period return relative, 2.0. And here's the second one, 100 divided by 200 is 0.5. Not minus 50%, not 50%, but 0.5. And now what does this say to do? It says multiply them together. So I'm going to multiply together 2 and 0.5, and when I do that I get 1.0. And then it says, okay, now take the nth root. Well, what's the nth root? Well, in this case, n equals 2. We only have 2 periods, so it's the square root. So I'm going to take the square root of 1. Well, the square root of 1 equals 1. And then this says, now subtract 1. So I'm going to subtract 1, and that gives me 0. Now, does that make sense? What was your annual rate of return? 0. You started with 100, you still have 100, 0. So we use the geometric mean approach. Now when you get returns quoted from a mutual fund, for example, they're going to be quoting geometric mean returns, not arithmetic mean returns, because geometric mean returns are always smaller than or equal to arithmetic mean. Let's give just an example of how that might be. I tend to think of it as, well, kind of like this. Imagine you have a field, and the field has sides of 5, the square. Well, 5 times 5 is 25, Square root of 25 is 5, okay. Now what if instead it were 4 by 6? So 4 and 6. Well, our area is only 24 now, not 25. And if we were to take the square root of that, what would it be? It would be less than 5. So what happens is, as our series of returns become more variable, our geometric mean ends up being smaller and smaller relative to our arithmetic mean. So let's take an example. Let's look at these numbers. 10, 14, 12, 4, 6, minus 10, 18, 1, 2, 3, 4, 5, 6, 7, 12, so that's 30, 20, 30, 42, 56, 66, 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay. Are we good?
There we go.
Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Give me a second just to make sure this works. 24, 36, 40, 46, 36, 36, 4, 6, 8. Okay. Okay, let's calculate the arithmetic mean and the geometric mean for this. To calculate the geometric mean, these are all returns, point whatever, 0.04, 0.06, 0.10, 0.18, 0.12, 0.14, 0.10. First, calculate the arithmetic mean. Okay, add them up and divide by 10.
9.
Okay, so while I was doing, the reason I was taking a minute is because I was trying to make it come out to a round number, which it did. So it's 0.09. Now, let's take the geometric mean. How do you do that? Now, we're going to have to add 1 to each one of these numbers. Now, that's easy to do for most of them until you get to this negative number. So it's going to be 1 plus minus 0.10. Well, what's 1 plus minus 0.10? 0.9. So this one is 0.90, but all the rest of them, you just add 1 to the number, okay? So multiply all this stuff out. 1.1 times 1.14, and don't do anything after that, just get to the product. So what number do you get?
2.31 or
Anybody get that number? Okay. Okay, so let's look back at our formula. What does it say? It says, get all those 1 plus r's, and that's what we did. It says multiply all those 1 plus r's together to get that product of them. And then it says take them to the 1 over n power. Okay, how are we going to do that? Well, we've got a y to the x key. So we're going to take it to the 1 over n power. 1 over n is 1 over 10, which is 0.10. So hit the y to the x key, y to the x, then 0.1 equals. Then what does it say to do? It says subtract 1. So minus 1 equals, and I get 0.0873. Okay, so before, I had 0.09. This is the arithmetic mean. The geometric mean is 0.0873. The geometric mean will always be less than or equal